Hi everyone, my name is Muhammad Arash bin Rahim from Intec Education College, Shah Alam, Section 17, and today I'll be teaching about current and resistance. This topic is one of the foundations of electricity. It explains how electric charge moves through a circuit and why some materials resist that flow, and how this affects the energy we use in daily life. By the end of this short lesson, you'll understand how electricity works inside wires, why resistors are important, and how this knowledge can even help you save money on your electric bill. Let's start with the basics. Imagine you have a simple circuit, a battery, a bulb, and some wires. When everything is connected, the bulb lights up. That's because electric current begins to flow. So, what exactly is electric current? It's the flow of electric charge through a conductor, usually through metal wires. In metals, those charges are electrons that move around freely. Now, there are two ways to describe the direction of current. First, conventional current, which flows from positive terminal of the battery to the negative terminal of the battery. This is the standard direction we use in all physics problems. Next is electron flow, which is the actual movement of electrons going from negative to positive terminal of the battery. Let's zoom in and see what happens to electrons inside the wire. They don't move smoothly in straight lines. Instead, they zigzag as they collide with metal atoms. Just like you walking through a crowded market, you move forward overall, but bump into people along the way. When the battery is connected, it creates an electric field inside the wire. This field pushes the electrons gently in one direction, causing them to drift slowly. The average speed of that drift is called the drift velocity, denoted by V. We can describe current with this formula using I, or current, equals to the number of free electrons per unit volume N times with cross-sectional area of the wire A times with charge of an electron Q times with Vd, drift velocity. This shows that current increases if there are more electrons, a thicker wire, or faster drift speed. That's why thicker wires are used for higher currents. They allow more charge to flow through, just like a wider pipe carries more water. Next, we move on to the current density. Now, instead of total current, sometimes we want to know how concentrated the flow of current is. That's where current density, or J, comes in, given by J, or current density, equals to the current I divided with area, or cross-sectional area. It represents how much current flows per unit area, measured in amperes per square meter. You can also express it as J, or current density, equals to the number of free electrons N times with charge of electrons Q times with Vd, or drift velocity. This tells us that the current density depends only on the material's microscopic properties. That is, how many electrons are available and how fast they move. Now, let's talk about resistance, the opposition to current flow. Every material resists the motion of electrons to some extent. That's why wires heat up slightly when current passes through them. The resistance of a wire is determined by R is the resistance equals to the rho, which is the resistivity of the material, times with L, that is the length of the wire, divided with A, cross-sectional area. So, a longer wire means higher resistance, while a thicker wire means lower resistance. Now, what is rho, or resistivity? Resistivity is a property of the material, such as copper. That is, it has low resistivity, or a good conductor, while rubber has high resistivity, which is a good insulator. One of the real-life examples is electrical cables in homes are made of thick copper wires to minimize resistance and prevent overheating. Next up is temperature and the relationship with resistivity. Temperature also affects resistivity. When a conductor gets hotter, the atoms vibrate more. These vibrations make it harder for electrons to pass, increasing their resistance. The relationship is given by ρ equals to the ρ naught in bracket 1 plus alpha, or the temperature coefficient of resistivity, in bracket the final temperature minus the initial temperature, close the bracket. So I can give you one example, that is when your phone charger becomes warm, its metal wires experience higher resistance. This converts some electrical energy into heat, which is why efficient chargers are designed to stay as cool as possible to prevent heat loss. Next, we have Ohm's law and ohmic devices. All of this connects to one of the most famous laws in physics, Ohm's law, which states V, voltage, equals to the current times with resistance. It means that voltage is directly proportional to current if the resistance stays constant. Devices that obey this rule, which is the resistance stays constant, are called ohmic devices, such as standard resistors. Their current voltage, or IV, graph is a straight line through the origin. One of the real-life examples is resistors in your phone charger control the amount of current going into the battery to prevent it from charging too fast or overheating. Lastly, electrical power and electric bill. Now, let's talk about electrical power, or how fast energy is used in a circuit. Power is given by P, or power, equals to the current times with voltage. And with Ohm's law, we can also write power equals to the current squared times with resistance, or power equals to the voltage squared divided with resistance. The unit of power is the watt, W, which equals 1 joule of energy per second. Here's when it becomes practical. The power rating of an appliance tells you how much energy it consumes per second. For example, a 60-watt light bulb uses 60 joules every second, while a 10-watt LED bulb only uses 10 joule per second. So, a smaller power rating means lower energy consumption, which helps reduce your monthly electric bill, as long as the appliance still does its job effectively. That's why energy-efficient devices like LED lights or inverter air conditioners are designed to do the same work with lower power usage. However, smaller power isn't always better. Some appliances need higher power to function properly, like water heaters or refrigerators. The best choice is not the lowest power, but the one that gives high performance with minimum energy waste. Now that we have come near to the end, let's summarize what we have learned today. Firstly, electric current, that is, the flow of charge through a conductor. Drift velocity explains how electrons move slowly in one direction under an electric field. Resistance and resistivity determine how much a material opposes current flow. Temperature affects resistance. High temperature means more atomic collisions. And Ohm's law links voltage, current, and resistance in a simple linear relationship. And lastly, power shows how fast electrical energy is used, and managing power wisely helps us reduce energy bills. Electricity powers everything around us, from phones, to transportation. By understanding current and resistance, we can design safer, more efficient systems and make smarter energy choices in our daily lives. Thank you for watching my presentation on current and resistance. I hope you now see that physics is not just numbers, it's the science that lights up our world efficiently. Thank you.